Alright guys, welcome into Unit 2, Lesson 8, Exponential Functions, IRL, which stands for in real life. Here's a couple pictures of Cha-Cha just to whet your appetite. As long as you stick around and watch the entire video, there will be more pictures of Cha-Cha, including a video of her being cheeky. You can see here she's quite cheeky. Very, very cheeky. Alright, let's get started. First question, which graph represents the exponential decay of a radioactive element? So by this point, you've already graphed a few exponential growth and exponential decay functions, and you should be able to recognize the shape of an exponential decay function. An exponential decay function is going to start high and then get lower and lower and lower, and it's going to increase over time. This one starts low, gets high, and then goes back down. This one starts low and gets higher and higher and higher. This is just a linear function. We don't like straight lines anymore. Not anymore. We're all about the curvy curves. 3 is your correct answer. We can see that it is starting high and getting lower and 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 lower. It's never quite going to hit that line because we have what's called a horizontal asymptote right there at y equals 0. But it still is technically getting lower, even if you can't see it. All right. Okay, so before we get started on the word problems, let's talk about some keywords we might be looking for. There are often keywords in word problems, and you've probably had some experience circling keywords to identify the type of problem being asked. We're going to go over a few keywords you'll be looking for to determine if a problem is an exponential growth problem or an exponential decay problem. So let's look at the easy ones. An exponential growth problem is going to involve increasing. It's not an R, but you get it. And an exponential decay problem is probably going to involve decreasing. Is it increasing at a rate or is it decreasing at a rate? If it's decreasing, you're decay. If it's increasing, you are growing. Things like doubling. If a population or something is doubling, that's going to be an exponential growth problem. Likewise, if something is being cut in half, and oftentimes, I don't know if you guys are there in science yet, it's more of a chemistry thing, but you deal with half-life. Half-life of an element is often the subject of an exponential decay problem. You'll see those a lot as we do the practice. Tripling is another one. Tripling means multiplying by 3. I hope you knew that. And dividing. If we're dividing something, then that's going to be a decay problem. All right, there's more examples, but these are the important ones. All right, let's get into our first problem. Suppose 30 flower beetles, don't know what those are, but let's roll with it, are left undisturbed in a warehouse bin. The beetle population doubles, there's a keyword, each week. The function f of x equals 30 times 2 to the x power gives the population after x weeks. How many beetles will there be after 56 days? Okay, so let's go back and highlight some key information here. This word doubles is letting us know that this is an exponential growth function. This population is going to multiply by 2 every single week. Now, we can confirm just by looking at this function right here, this is an exponential function because our variable x is in the exponent as opposed to being raised to a specific power. And we also know that this is a growth function because our b value is 2, and 2 is greater than 1. Whenever our b value is greater than 1, we know that this is going to constantly increase at a greater and greater rate as we move forward. All right, let's get into it. How many beetles will there be after 56 days? So you might be thinking, okay, let's plug 56 into x, but not so fast. We've got to be careful here with the units. 56 days is a big number, and it's not asking for how many days. X does not represent days. X represents weeks. This is a tricky problem. This is annoying. I hate it when they do that. It really just like relies on you being able to spot these things that are like kind of deliberately misleading here. So hopefully as you read through quick enough and you notice the difference between days and weeks here. All right. How many weeks are in 56 days? 56 divided by 7 equals 8. Okay. This is our x value, 8. So 56 days is 8 weeks. We're going to go ahead and punch that in. 30 times 2 to the power of 8. I'll give you I'll do the same thing so you don't have to pause the video. 30 times 2 to the power of 8. We end up with 7,000, what the heck? 7,680 beetles. Oh, good God, that's a lot of beetles. Please no. All right, just to double check, let's go ahead and with 30. After 1 week, we've got 60. This is what I love about calculators. If I just keep pressing enter, it keeps doing the same thing. After 2, it's 120. 3 weeks, 4 weeks, 5 weeks, 6 weeks, 7 weeks, 8 weeks, boom, 7,680. Makes perfect sense. All right, let's move on. All right, moving on to our next one. Initial population of 20 rabbits triples every half year. The function f of x equals 20 times 3 of x, 3 to the power x half year periods. In these problems, for many reasons, but typically it's because rabbits are known for reproducing quickly. So if it's a rabbit question, it's probably going to be an exponential growth question. Just understanding what rabbits are known for. All right, so this one, it triples every half year. That's pretty good. That's a prolific populator. How many rabbits will there be after 3 years? So with these questions, it's always important to see what x represents. X is a half year period. How many half year periods are there in 3 years? Well, there's 2 half year periods in a year. So 3 times 2 gives you 6 half year periods. This is my x value. Let's go ahead and plug it in. Whoops, I missed. 20 times 3 to the power of 6 equals that's a lot of bunnies. 14,580. You know, bunnies are actually considered pests in Australia. Those ones weren't too bad. They gave us the function, which is always nice, so it really just came down to figuring out what our x value was and then plugging it right back in. But normally they're not going to give you the function when they give you these problems. They're going to give you something like this one down here. Suppose the population of deer in a region was 3,500 in the year 2000. Yeah, population is always going to be an exponential function for the most part. Since then, the population has grown by 3.5% annually. What will the approximate population be in the year 2020? All right. For this problem, it's asking you to write the function first before you can actually do anything with it. So let's look at our regular formula. Y equals A times 1 plus or minus R to the power of X. Okay, that's a lot there. Let's start to unpack it. So Y is Y. That's going to be our vertical spot. That's you know, half our coordinates on the graph. There's nothing special there. A is our starting value, or initial value sometimes it's called. So in this case, let's go ahead and build the function for this situation one bit at a time. Suppose the population of deer in a region was 3,500. So my starting value is 3,500 in the year 2000. Okay. R is the rate. Now, you may have noticed that the rate is, it's got this plus or minus symbol right here. So, the rate, the symbol that you use, plus or minus, depends on if it's a growth function or a decay function. If it's a growth function, you are going to add the rate to 1. If it's a decay function, you are going to subtract the rate from 1. But it's always 1. We'll talk a little bit more about why exactly that is later. Maybe I'll do that as a discussion question for you in class. All right, so rate for growth, use plus. For decay, use minus. All right, so the rate is 3.5%. So 3.5%, whenever we see a percent, we're going to have to convert it to a decimal. Hopefully you remember that we convert decimals, convert percents to decimals by simply dividing it by 100 or moving the decimal point 2 places to the left. So this is going to be 0.035. So that's my R value. Since this is a growth function, that means we're going to add it to 1. So 3,500 times 1 plus 0.035 to the power of x. All right, we have our function. It was that simple. Oh wait, we actually have to answer the question now. What will the approximate population be in the year 2020? Okay, well, if they started in the year 2000, we're asking how many years have passed when we get to 2020. Show your bet.
No. Yeah. Inappropriate, Samuel.
Indeed.
Here, I'll put this mirror up higher so you can use it.
All right, let me start the video again. All right, once we punch it into our calculator, we can put these together. 3,500 times 1.035 to the power of 20. All right, this one I'm going to get some help from you. Well, metaphorically, I can't talk to you while I'm doing this video, so I'm just going to assume that you're following along and answering these questions on your own. Adrienne invested $2,000 in an account at a 2.25% interest rate, compounded annually. She made no deposits or withdrawals on the account for 4 years. Determine to the nearest dollar the balance in the account after the 4 years. All right, so let's go ahead and pull up our previous notes. We have y equals a, our starting value, times 1 plus or minus r to the power of x. All right, so Adrienne invested $2,000 in an account. So if you're investing money, typically you want to get a return on your investment. Your money should grow. If your money is shrinking, then you've made a really bad investment, and you shouldn't be doing that. You should always be trying to make more money with your investments. But hey, you know, the economy is a little wild. Sometimes things go poorly. Either way, in this case, we have a 2.25% interest rate. That means that it's going to grow every year by 2.25%. So our initial value is 2,000. The video didn't skip. You're going to do plus or minus here. Well, is it growth or decay? This is growth, which means that we are going to add the value of r. Now, what is r? So 2.25%, we're going to convert that to a decimal. So 2.25, let's take that decimal, bloop, blop, add a 0 here. R is 0.02, complain it. 1 plus 0.0225 to the power of x. X is always just going to be x there. We don't have to worry about x. That's all good. All right. All right, since this... stupid truck. All right, since this is compounded annually, that means that x is just the number of years. And if we're doing it for 4 years, that means 4 is the value of x. So there we go. We got it. Let's punch it into the calculator. 2,000 times 1.0225 to the power of 4. And we get $2,186.17. It asks us to round it to the nearest dollar. So let's just... Alright guys, here's our final problem. Aw, I know, you're having so much fun, but here we go. The value of a car purchased for $20,000 decreases at a rate of 12% per year. What will be the value of the car to the nearest cent after 5 years? Come on, Regents people, can you just be consistent? Do you want it to the nearest dollar or the nearest cent? Why are you trying to mess with us? So frustrating. Anyway, $20,000 decreases, rate of 12%. We got a lot of information to go on. Let's go ahead and build our function. Y equals a times 1 plus or minus r to the power of x. All right, my starting value is $20,000. That's right, 2000. All right, times 1 plus or minus, right? That is the question. Are we plussing or are we minusing? Well, is this going to be a growth or a decay? Say it with me on 3. 1, 2, 3, decay! I hope you said it out loud and you made the people on the bus or the train or wherever you're watching it a little confused as to why you just shouted randomly. If not, that's okay. I don't blame you. Alright, so this is decay. We're going to use minus instead of plus in this case. And we're going to get an r value here. So since r is 12%, 12% as a decimal is 0.12. So 1 minus 0.12 to the power of x. Alright, so this one's a little trickier. Well, no, it's really not trickier. We just plug this in here. Alright, so it is asking us what the value of the car will be after 5 years. So if x represents the number of years, then we simply just replace x with 5. Hooray! And we use our trusty calculators. We're going to do 20,000 times 1 minus 0.12. So 1 minus 0.12 is, I know what it is. Do you know what it is? There it is. 0.88 to the power of 5. Whoops, times 20,000. Doesn't matter what order you do it in. You end up with $10,554, and this one asked it to the nearest cent, and 64 cents. Alright, so this car is worth almost half of what it was 5 years ago. To be perfectly honest, that's a pretty good depreciation rate. Typically with a car, you lose about half the value as soon as you drive it off of the lot. Maybe this was a used car when they bought it or something. Maybe they weren't using it too much. But that would be pretty nice if you're able to get some 5 years worth out and still get about half your investment back. That'd be pretty nice. I've never been able to get that deal. Anyway, thanks for watching.